Hello, everyone. My name is Vineet Shenoy, and I'm with Johns Hopkins University presenting Unrolled-iPPG, video heart rate estimation via unrolling proximal gradient descent. This is joint work with Tim Marks, Hassan Mansour, and Suhas Lohit at the Mitsubishi Electric Research Labs, where I was an intern. Consider a clinic of the future, in which your heart rate is automatically determined before you see the doctor, or heavy equipment operation, where the operator's heart rate is remotely monitored for any rapid changes. This is the problem that we are focusing on, remote heart rate estimation. We define the problem such as this. Consider an RGB video of n frames and its corresponding ground truth pulse signal y. Then, given only the video v, we hope to reconstruct the pulse wave y and determine the subject's heart rate. We take a modular approach to this problem. We first perform face and landmark detection, where the landmarks identify key points on the face. We then expand the number of landmarks and extract a time series from 5 different segmented regions on the face. We assume that these time series contain the pulse signal in noise. These time series are then passed to Unrolled-iPPG, which is to separate the pulse signal from the noise. Finally, with these clean signals, we estimate the pulse rate by taking the Fourier transform and finding the peak. The key to our algorithm is to extract a time series. And we do so by first passing each video frame through a phase detector such as face boxes, followed by a landmark detector, which is Lovely. Lovely generates 68 fiducial points on the face. We then assume that there's pulsatile signal in the cheeks, chin, and forehead, and extrapolate the number of landmarks to 145 landmarks. We then segment the face into 5 spatial regions, and we take the mean pixel intensity of all landmarks in a region across all frames to generate a 5-channel time series. We assume that this 5-channel time series contains the pulsatile signal, but also contains noise. And we then must separate the pulsatile signal from the noise. We follow the work of previous paradigms, such as auto-sparse PPG, which also models a 5-channel time series Z as the sum of some pulse signal Y plus noise, or equivalently, the inverse Fourier transform or the Fourier coefficient of the pulse signal plus noise. Autosparse PPG assumes that the Fourier coefficients X are sparse, and that the noise is only present in a sparse set of regions. They then formulate this as a sparse optimization problem with the goal to recover X and E. This optimization problem can be solved via iterative shrinkage thresholding algorithms, which alternate between gradient steps on the data fidelity term, followed by a proximal operator, which in this case is the soft thresholding operator. This algorithm is run until convergence to solve for the pulse signal. As opposed to autosparse PPG, we take a different view, where we don't explicitly define sparsity priors, but define an implicit prior rho of X and E. We then must have corresponding proximal operators, R and Q. Our optimization problem is in the same style of ISTA and autosparse PPG. Therefore, we can use the same training paradigm as ISTA, where we solve for X and E using alternating gradient update steps, which are in the red box, followed by proximal operations, which here we call denoisers, where we pass X through the network feed-forward neural network R, and E through the feed-forward neural network Q. We run these alternating gradient and denoiser steps for capital T iterations before we compute an MSE loss between our reconstructed pulse signal X and the ground truth pulse signal. We then compute the gradient of the loss with respect to the parameters and update the parameters of the network. This problem formulation achieves state-of-the-art results on the MMSE-HR dataset. This dataset is composed of 102 videos of 17 male and 23 female subjects and is captured at 25 frames per second. We then define 3 evaluation metrics: the mean absolute error, root mean squared error, and the PTE6. The mean absolute error and root mean squared error are defined as the difference between our estimated pulse rate, R hat I, and the ground truth pulse rate, Ri. While the PTE6 is a quantity defined to determine how many of our pulse rate estimates are within 6 beats of the ground truth, and this is expressed as a percentage. Using this data set and this set of evaluation metrics, we show that we achieve state-of-the-art results using Unrolled-iPPG. Our results show that we perform better than traditional signal processing methods like ICA, Chrome, and autosparse PPG, as well as we perform better than traditional deep learning methods such as CAN and inverse CAN. We show that hybrid signal processing and deep learning methods perform best. We also show qualitative results. In all diagrams here, the blue signal is our empirical signal, which is passed through our algorithm, while the orange signal is the ground truth. The top row is our empirical signal before running our algorithm, while the bottom row is our empirical signal after our algorithm. What we can see is that in the time and frequency domain before our algorithm, the signal that we have is noisy, and it contains erroneous frequency peaks that does not capture the true underlying pulse rate. However, after our algorithm, we not only capture the true pulse rate as shown in the frequency plot, but we also attenuate the spurious peaks. In the time domain, we see that we eliminate much of the noise and generate a periodic signal. This shows that our algorithm can take a noisy pulse signal and denoise it to the correct statistics of the underlying pulse signal. We also show the results over multiple time windows. Here, we take 7 consecutive 10-second time windows and run our Unrolled-iPPG. The blue is our predicted heart rate, while the orange is the ground truth. We show that our algorithm can correctly predict the heart rate over multiple time windows consecutively and over a large range from approximately 75 beats per minute to 92.5 beats per minute. We conducted an ablation study to understand the number of unrolling iterations that we use before computing a loss during training time, or before we output the results during inference time. We studied the number of unrolling iterations corresponding to 1, 3, 5, and 10 unrolling iterations. And we see that 3 unrolling iterations provides the lowest MAE and the highest PTE6, while 1 unrolling iteration provides the lowest RMSE value. We also conduct an ablation study to understand the effect of explicitly modeling the noise. The top optimization problem does not explicitly model the noise and only optimizes over the frequency coefficients of the pulse signal X, with the corresponding implicit prior operating only on X. The bottom equation is our standard formulation in which we model both the noise and the frequency coefficients of the pulse signal. Table 2 shows the results, and we see that when we do not model the noise specifically, our performance is worse in all 3 metrics of MAE, RMSE, and PTE6, while modeling the noise explicitly improves all metrics. One caveat here is that when we explicitly model the noise, we increase the number of parameters, increase the memory footprint, and increase the training and runtime of our algorithm. So these are important considerations to make if these algorithms make into real world practice. We conclude by demonstrating that our hybrid signal processing and deep learning method can estimate the pulse rate as well as the pulse wave from facial video. Our method is able to use small convolutional neural networks that correspond to operators of some implicit prior. And we show that we are able to achieve state-of-the-art heart rate estimation performance on the MMSE-HR dataset. And it showed that our algorithm is superior to both traditional signal processing methods as well as purely deep learning methods. Finally, I'd like to acknowledge my mentors who provided invaluable guidance during this project. I'd like to thank Tim Marks, Suhas Lohit, and Hassan Mansour for their invaluable guidance and insight on this project. If you have any questions about this, please talk to me during the ICIP conference this October, and I'd be happy to answer your questions. Thank you for your time.